It's weird. I gotta keep checking. I'll keep stopping for a second. So mg cosine theta, and then the parallel component's gonna be mg sine theta, right? And so let's just take this, let's take our free body diagram and let's just rewrite it. So there's our object, and now we're gonna have the parallel component's gonna be mg sine theta, and there's normal force and mg cosine theta, right? So that in our using our fancy 10-cent word, that we just orthogonalized the free body diagram. We took all of the forces and broke them into components, and then put the components on the free body diagram instead, right? So then what's going to be the answer to part one? If the weight mg is just 71.3, isn't it? Right? Yeah, I'm just going to, what's a calculator number, isn't it? I just multiply that by sine of theta, which is 16.8. Okay? So we get 71.3 times sine 16.8 is that calculator number. So how many sig figs we keeping? 3. Okay, so what's our answer going to be then? Yeah. So 20.6. What are my units going to be? It's a weight, so that's a force, right? So newtons. Okay. And then the component of the trunk's weight perpendicular. Well, that's going to be the same thing, right? I'm just going to take that last calculation and turn the sine into a cosine. And so I get, what's that, 68.3 newtons? Okay. And notice how the points are spread out here. So that's, most of the points are the first two parts, and then now only 6 of the 24 points are coming from the last one. So now we want to know, after 2.33 seconds, the trunk will have moved a distance of what? Okay, that's just kinematics, isn't it? Right. But what do we need to know? Acceleration. Good. Okay, so then all we got to do here is we need to know what's the acceleration down the ramp. Well, let's look at our free body diagram. What's the net force acting in the parallel direction?
mg sine theta.
mg sine theta. That's it. There's only one thing, right? So then our equation of motion is pretty simple here. It's just going to be mg sine 16.8 equals, net force is equal to what? ma. Right? So the m's I can cancel. And a is just equal to g sine 16.8. Okay, so that'll be a calculator number. And then we can just do kinematics, right? Let's write down the stuff we know. So we know acceleration is, well, something. Let's see what it is. So it's 9.8 times sine 16.8. So it's that number. So roughly 2.83. Standard units, right? And then what else do we know about this? What's the initial velocity? 0. Do we know? We don't know anything else, do we? That's really all we know, right? Initial position. So we're really just looking for, was it displacement? Can't remember. What's it asking for? I've moved a distance up. Okay. So then, what's the kinematic formula we're going to use? Number 3. Yeah, exactly. And number 3, the initial velocity is 0, so that gets pretty simple, doesn't it? It's just going to be delta D equals V naught T but that's 0 plus 1/2 a t squared. Hold on, is that the one we want?
Yeah.
Let's see. Oh, they give us a time, don't they? Yeah, they give us a time. 2.33 seconds. Yeah, so t equals 2.33, so I'll just plug that into my calculator, right? And I can even just use the calculator number that I've already got there. So we're going to do 1/2, so I'll just make it 0.5 times my acceleration, which is right there. We agree that's the number that we used for acceleration, times the time of 2.33 squared. There it is. So we had 3 sig figs, right? So what's that going to be? 7.69. And we were measuring displacement, so it'd be, what would standard units be? Meters. Right? Make sense? And that's a pretty good problem. Right? There's a lot of stuff there. Okay? Questions? We good? All right.
Wait, so was the mg sine theta, was that for parallel?
Let's look at the picture and see. So we said that there's the theta, right? So then we know that the perpendicular is going to be the adjacent component. So that's going to be the cosine one. And the parallel is the opposite, so that's the sine. Right? So the 20.6, the parallel component was mg, which, what was that? 71.3 sine theta. Okay. Okay. All right. Next. Okay, 106 Newton weight is supported in a motionless position by 2 ropes that each make an 18.2 degree angle with the horizontal. So what's the tension in the rope, right? So what's our picture going to look like then? So if this is the object, right? Here's the horizontal. What's that mean? In what direction are the tension vectors pulling? Okay, good. Kind of out to the side, and the angle between the tension vectors, right? Because that's what's holding it up, right? The tension in the line, and the horizontal is 18.2. So we get this. There's T, and that's 18.2, and there's T, and that's 18.2, right? And then what's the other force acting? Yeah, the weight. Okay, so the weight's pulling straight down. Okay, so what's going to be, what directions would we use here? Up and down and side to side, right? So X and Y. So we got to take these tension vectors and break those into components, right? Okay, so how about, let's, just because it's hard to draw that, let's call that theta to make things a little bit easier. And so we're just going to we're going to replace tension vector with its components. So we're going to have a big horizontal component. What's the horizontal component going to be then? That could be a cosine or a sine. Cosine, right? Because it's adjacent. Okay. So that's going to be my t cosine theta. The vertical one is going to be my t sine theta. I got the same thing going on over here, right? Everything's just mirrored. So that'll be a t cosine theta, t sine theta, right? Okay, so now we want to take, and everybody sees this process here. We've done this a bunch of times, but does everybody get that the next step would be to take that free body diagram and then just draw it with only the components? So all the vectors or components of vectors are pointing in convenient directions, right? So we go from here to something like this. Okay, so what do we have going here? We've got t cosine theta T cosine theta, right? That's not very helpful. What's gonna happen to the horizontal components of the tension? Yeah, they just cancel, right? Okay, but vertically, there's something different going on. Vertically, what am I gonna do vertically here? So I'm gonna take this vector and scoot it where? Okay, you're right, I'm gonna translate it so it's sitting in the right spot. So it's starting at the object. So there's gonna be a T sine theta. So what am I gonna do with this one then? Same thing, but I always add vectors tip to tail, right? So I'll just line that one up right there. Does that make sense? So how long is that whole vector then?
T sine theta times 2.
Yeah, just 2t sine theta, right? If I add them, t sine theta plus t sine theta is 2t sine theta. And then down here, there's our mg, right? Okay, which we know, it's 106 newtons is the weight of this thing, right? So what's the important equation of motion then that we're going to get out of this? This one doesn't really help us much, right? The net horizontal force is just t cosine theta minus t cosine theta equals 0. Well, that doesn't help. But what about vertically?
So 2 T sine theta.
Ah, okay, good. So we get this guy, so 2t sine theta in the positive direction minus mg equals.
0.
Okay, but think about this situation. Is anything moving?
No.
Ah, it's static, isn't it? It's a static situation because the thing's just hanging there. So there's no acceleration. So it's 0. So all I have to do to solve for t then is what? Right, I'm going to push that mg to the other side, right? So we get 2t sine theta equals mg, and I'll just divide each side through by 2 sine theta, right? And that leaves me with the t by itself, and so that's just a calculator number. Right, so then we'll just go plug that stuff in and see what we get. So what were those numbers? So we get 106 is mg. So 106 divided by, now I got to put this in parentheses, right? Everybody see why?
What about grain or gravity?
Okay, yeah, but see, you're right, but is that the mass? 106 newtons? No, that's the weight, right? That is mg. Everybody see that? Because they're giving us a weight, not a mass. So the g is already incorporated. I know that mass times, m times g is that, right? You can call it F sub g if you want to call it gravitational force. I always call it mg, just because you remember, we know that that's what the gravitational force is, right? What weight is. So there's my 106 divided by, in my calculator, I must put it in parentheses, right? Because I'm dividing by the whole denominator of 2 times sine 18.2. And got to close the other parentheses.
Do you ever use the fraction button?
You can. You certainly can. I just, it makes it really small, so I usually don't. So I end up getting a big number like that. Does that make sense? It does, doesn't it? Remember our discussion earlier about how the ice can like rupture power lines and stuff because a very small, and then we talked about how you could free your four-wheel drive if you get stuck in the snow or something, if you had just a tow rope and, right? A very, very small force perpendicular to, something that's almost straight creates really large tensions, doesn't it? Right? That's a really ineffective way to bear that load with that tension. Only a small portion of the tension vector is actually doing useful work and actually supporting the picture. So the tension is big, and it should be. Rounded to how many places we got? 3, I think? Yeah, 3. So
the tension, okay, so if you had a tight line, there would be less tension, right? Straight. And then the more angle, the more tension.
The smaller the angle, the bigger the tension.
Oh,
right? So if you wanted to, and that's useful to know about, right? So if you wanted to, what if you really did want to hang something on your wall?
zero angle is the least.
Is going to be the most. That's going to be the most tension because look at this angle, right?
Okay.
See what I'm saying? That look at this answer we get here. We didn't even put an angle in. If I put in, think about what a sine function does. A sine of a really small angle is really small, isn't it? Right. So I'm going to be dividing by a smaller and smaller number if I make the angle smaller, which makes the overall fraction a lot bigger. Right. And so the physics is telling you, if your mom wants you to hang a picture for her on her sheetrock, and you're gonna put the cable on the back of the picture and stuff, do you want to just tight line that thing and have it be really? No, you don't, right? Because that's likely to break the cable or break whatever. That's a lot of tension involved just hanging the weight. You want to have a little bit of a downward, some slack in the line so there can be a little bit of an angle there, right? Or it could be really high tensions. Okay. All right. Okay, so on to projectile motion. Okay. So what about this one? We've got this stone that's launched horizontally, and they give us the initial speed, and they tell us how tall the cliff is. So we want to know, how long does it take for the stone to reach the ground below? So now these are the ones, and these are really important questions. We talked about this, but it's been a while, so let's kind of go back. And the nice thing about learning is every iteration through the process makes the whole thing a lot easier, right? Because now you've done this before, you've got some prior knowledge to build on, you've got some scaffolding in your brain, there's interconnectedness that's going to help you out. So this will be, if it was at all difficult before, this time through, I bet it gets really easy. Let's maybe draw a picture. Can't hurt. So here's our cliff. Right? And the height of the cliff is 73.1. And the path of the projectile is just going to be something kind of like that, right? Everybody agree? Okay, so what we really want to do then, remember, for projectile motion, we're just going to break this into horizontal and vertical components and treat them independently. The only thing that's going to link the two is time, right? So if we break this into our horizontal part and our vertical part, what do we know vertically? Vertically speaking, what's the initial velocity? 0, right? Vertically, it's starting from rest. It's only got a horizontal velocity initially, right? So V naught sub y is 0. What else do we know vertically? Okay, so and so the acceleration vertically is what? Negative 9.8. Good. Okay. What else about this trip vertically? Okay, so the displacement. So delta y, our displacement is what? 73.1. Careful. Negative 73.1. It's going down, right? In standard units, right? And what are we really trying to find? Time, right? Time's the big thing. We want to find time. And so we can do that just from the vertical picture. Which one are we going to use? Two's not going to work though, because we don't know the final velocity, right? See what I'm saying? Which one are we going to have to use then? 3. Yeah, we're going to have to use 3, aren't we? But 3's okay, because it gets easier, because look, the first term's going to drop off, right? Because the initial velocity is 0, right? So we'll use equation 3, which is delta y equals v naught sub y, right? The y component of the initial velocity times time plus 1/2 a sub y t squared. Fortunately, that goes away, right? And so what do we end up getting then? So we end up getting delta y equals 1/2 times a. That's just negative 4.9, isn't it? Everybody agree? If I just take this part right there, that's negative 4.9 t squared. So what would I do to solve for t then?
Add 4.9 squared.
Not add, divide, yeah, because what I've really got here, delta y, we could plug in a number there, couldn't we? Let's do that. What is delta y? Yeah, negative 73.1. Those physics guys are pretty smart. When we divide a negative by a negative, we get a positive, right? So t squared equals 73.1 over 4.9. We can cancel the negatives, right? Negative over negative is positive. And so we're just going to use our calculator and figure out what that is. So t is equal to the calculator number, the quantity 73.1 divided by 4.9. I guess I didn't need to do that. So there's our number. We take the square root of that, right? So square root of that number. Technically, I'd have to do plus or minus, but obviously, which one do we want for time? The positive one, yeah. So we'll take the positive, and it's about 3.86. Okay, and we'll leave that in our calculator. But we get this number. Oops. Okay, that's good. That's the first answer to our problem, but it also helps us out, because now if we move over to the horizontal side of things, what's going on with the horizontal side? What's our initial velocity in the x direction? 9.95. Good. So v naught sub x is positive 9.95. Anything else we know? Is there any acceleration? Nope. Nope. Right, because it's projectile motion, right? It's constant velocity. And so this is actually v sub x too, isn't it? Right? We want to know how far does it land from the base of the cliff. Well, isn't that really just delta x? Right? But what's delta x? Which one are we going to use for that? That's an easy one.
T equals pt.
Yeah, top one, right? Okay. So delta x equals v sub x, average one, but it's the same thing. It stays the same. So v sub x times t, which we know, right? And so all we have to do is plug that stuff in, right? So we get delta x equals, what did we get here? 9.95 times our time. 3.86, but we'll use the calculator number, right? So we get, oh, come on now. So we get that number times 9 point, oh shoot, forgot the times. That number times 9.95 gives us that, right? So the answer to part 2 is 38.4. So we can fill some things in. So this one was 3.86 seconds. This one was 38.4. It was 3 sig figs, yeah, meters. And then what about the speed? Last part. To find the final speed of this thing when it hits the ground, all we'd really have to do is just find out what the vertical speed is and the horizontal speed is, and add those up as vectors, right? Well, the horizontal component stays the same, it's 9.95. To find the vertical one, we could use, for example, this guy, number 2, right? And we could just say, all right, so v sub x, or v sub y, just equals the initial velocity, which is 0, plus a sub y times t. A sub y we know, that's negative 9.8. T is 3.86, right? So we could add another quantity up here to our column. V sub y equals, another calculator number, negative 9.8, right? There's our acceleration. That's all we're doing, just a sub y times t, which is that number right there, wasn't it? Yeah. So there's our vertical velocity, negative 37.9-ish. We got it in our calculator. And if we want to find the final velocity, then all we've got to do is just add these two vectors. Let's make this one orange, right? So there's the horizontal velocity. So 9.95. Let's make this one green, how about? The vertical velocity is negative 37.9. Right? And so the resultant final velocity then is going to be that. Everybody agree? How would I find it? Pythagorean theorem. Yeah. So we'll just go come on. So we'll go the square root of 9.95 squared plus 37.9. Now look, that one's negative, so I'm going to put it in parentheses, right? In parentheses, we'll grab that. Close parentheses, square it. Remember, we have to put negative numbers in parentheses. And we end up getting 39.1 to 3 sig figs. Okay, so that's the final velocity when it hits the ground, the magnitude of velocity at least. That's all they want is the speed, right? So 39.1, and they already provide the units, meters per second. Make sense? Okay? All right. Are we about done? When are we out of here? 10 after? Okay.